correlations. Okay. Yeah.
So I know some of the missing slides, so I try to emphasize a few points. First of all, I think that disappointment was due to the fact we couldn't prove without a doubt break-up correlation. But it is not fully disappointing because we found out probably something which is profound in weak measurement, and it opens the way for a new kind of non-local correlations. So this is the first point. The second, you rely on a successful interpretation of the interaction-free measurement, the Hardy experiment, and even ordinary and weak measurements with the help of understanding uncertainty. And what you say in the oblivion example is when two particles transfer some physical quantity and this quantity is very uncertain in one of them, then forgetfulness occurs. And probably this is something which is very broad in the quantum realm, and it enables also weak measurements. Now, regarding weak measurements, what we understood during the last talks that post-selection enables to highlight the past uncertainty. It rearranges the result in a way sliced by the future measurement. So this is again, but this is a repetition, but what you are trying to say, I think, is there is something more than the uncertainty we see. You find an underlying reality in which there are two, like in Lev's experiment, two beams of photons, one with positive projection and one with negative. And I just end with a speculation because I didn't thought about this before. The simulation Lev showed had 3 peaks with the same height, but the experiment showed that the peak with the negative width value was slightly shorter. And this is a phenomenon we can't explain using ordinary quantum mechanics, but this is just wild speculation.
Thank you very much. So I'll reiterate what Eddie said, and this is once again I have to apologize for the mishap with the presentation. Then otherwise it would be much more clear. There is a work of us called Quantum Oblivion. You can find it on the web, in which we show that in all measurements there is this kind of interactions, a series of interactions going on between the particle and the mirror in this case, but it could be any sensor. And very interesting things are happening at the very brief time. Imagine a probe being smeared over space, being both in the front and at the rear, and in all the cases in between. And then the particle interacts with it not once, but several times, such that position and momentum measurements become somehow intertwined, and if you do not interfere, which usually is what we do, then you get a pure momentum result, and then you think that either nothing happened, there was the Hardy paradox, or the IFM, and so on and so on. This work, please consult it. It is on the web, and there is nothing revolutionary in it. There is just later understanding of things known already. What Eddie is now saying is that there was a surprise that we found even in Lev's lecture, that I believe that in his slides we can see that when you go, and that was perhaps the main message of my talk, when you do a kind of can I call it meso measurement, that is, you take a strong measurement and make it weak. So apparently you can't have the cake, eat the cake and have it eaten, right? The more you eat the cake, then you have it no cake. There is a slight case in which you ate a lot of the cake and there is still a lot of the cake. And that is the case in which those negative momenta turn out to be part of the correlations. I believe, we are not sure, that something in your data even indicated that. We can look at this later. So this is very speculative, but we feel strongly about it. Is that what you wanted to say? Yes.
Okay, Ruth next. But could anyone else with questions just re-raise your hand? So maybe it's,
Did you say me?
Yeah.
Oh, thank you. Okay, yeah, well, I appreciate your considering the transactional picture, and I guess in view of the fact that I'm an advocate of the transactional interpretation, in your presentation, I really wouldn't identify as a single state person. However, I still think that a person who wanted to go with standard orthodox quantum mechanics would be able to answer your concern about the three-box paradox by noting that in that case, you're dealing with an amplitude, again, a transition amplitude, and amplitudes can be negative. And so the component that is associated with box C can just be viewed as a negative amplitude wave function rather than a particle with negative, mass and that kind of thing. So that's just a suggestion of how they might.
No, but they're not active. There are experiments, like Steinberg's experiment. With weak measurements, you send an electron to the box in which there is to one of the three boxes weakly. And then overall you get the strange result that the single electron that you began with resides in the two boxes, whereas, Ruth, in the third box, it attracts the other electron rather than repels it. Now, you wouldn't say that it's a positron there, right?
Well, I don't know if, again, it's a statistical effect when you get
Oh,
this
come
right.
on. But everything is, when we talk about, you're not going to give me this. In weak measurements, everything is statistical.
Okay, so you're saying that you're actually measuring the mirror or something on each run?
Think about the three boxes. So there's an electron in the three of them. This is Steinberg's experiment. And then weakly, you measure the presence of the electron by sending another electron, probe electron, towards that box. Then they proved, statistically of course, that in the first two boxes the electrons were repelled. In the third box, the electron was attracted, slightly
And this was after post-selecting for certain ensembles?
Right. But remember that now what we claim is that even before post-selecting, you can see a slider, but still there. So, probabilities, amplitudes, and so on and so on. Don't you think that I was correct when equating this to what Dirac did when he said, if this is what the formalism says, let's attach it to some physical value. And I can't do it to the charge, so I'll do it to the mass.
Well, I'd have to look at the details of the paper, but again, in terms of the transactional picture, you're going to have 3 different transactional opportunities corresponding to each box, and this does take into account the absorption, and that plays a role in the kind of phenomena that you're going to see.
And would you consider my proposal for a rejection wave being
We'll have to look at that too.
Sandy has a point on this.
Yeah, I just want to make a comment. It seems that there is a slight misunderstanding about weak measurement, thinking that always they have to be very weak, and always are almost random and things like this. That is absolutely incorrect. So if instead of a single particle in 3 boxes, you would have many particles, which would be then a rare event that you post-select all of them in the same state, then your measurement can be actually very strong and still indicate.
Of course.
And that is exactly the point that also James Lehman did with a large value of the spin, where square root of n is much, much smaller than n, then it can be very, very robust. No need to be almost random.
So thank you very much for that. Again, a finger by both.
Yeah, I just want to be clear that I didn't say that, and I do want to point out that weak values are defined independent of any kind of measurement. And in that sense, it's a bit of a misnomer. And I didn't mean to suggest that a particular way of measuring them. But I did also want to point out that the time symmetric, the two-state vector formalism is equivalent to standard quantum mechanics. And I think Professor Harnov has made this point, that whatever results you get from the time the two-state vector formalism, you have to be able to get from standard quantum mechanics. I just want to...
Right, let me just say where I do not concede the fit yet. I consider the fit on some parts, but this is where I do not concede the fit. I'm still sure, and I can prove it, that it will be possible to show another version of this experiment in which the one vector formalism will turn out to be not incorrect, but involves such a kind of conspiracies that it would be thermodynamically ridiculous or cumbersome or something like that. We don't have something like that yet, but I still have a feeling, and it's a promise that I have to fulfill, that it will be possible to show something like that. Let's wait for Reykjavik or Alaska or whatever. If I'm still invited.
Matt, did you have a question?
Yes, you said that the one statist has to accept negative, photons carrying negative momentum in order to explain the correlation between the cases where the mirrors went inwards. Right? Why can't they just say, yes, mirrors going inwards is an error, but it's an error that becomes less likely if the photon kicks the mirror outwards. And that's why there's a correlation between
Can you
cases.
repeat that? I love it. Can you repeat that, what you said now?
So when you measure the mirror as having moved inwards, that is an error, but it's an error that's less likely if the mirror is being pushed outwards by the photon.
Are you suggesting
so-
that there are systematic errors?
it's just like if you have a mirror that jumps in some random direction, but you've already pushed it this way, then the chance that the overall effect is that way is
Well,
going to be
consider the
reduced.
case, no. So what I would advise is the following. Consider the case in which there is no photon, and there are just two mirrors like that, okay? Then you will see that the presence of the photon, who affects both of them at the same time, is making a difference in the probability. So so it's not just, if you were talking about an error, that is a systematic error, which is an oxymoron that I don't think that you want to go that far, do you? This is what I was hoping to show when I talked to Ruth. People would have to invoke some kind of conspiracy between errors. Do you understand what is a conspiracy between errors? You don't want to elaborate on that, right? Well, what I'm talking about is that the remedy can be worse than the disease in that case. So this is why I think, yeah, if you tell me that your alternative as a one-vector formalism to negative momenta is systematic error or correlation between the errors, I would be very happy. I'm not sure that you would be very happy with that.
Yeah, I'm saying it's a correlation between the errors, but it's one that has a perfectly natural explanation.
But then you have something
The
which,
photon just makes the error.
but then you wouldn't have it without the photon going between them.
Yeah, but neither would you.
Sorry?
Without the photon, you wouldn't have the correlation either.
So it's a strange systematic error.
Yeah.
Actually, think about it as a kind of teleportation. Okay, you have a quantum object, which is the mirror, another mirror, and there is one photon which entangles them. So a property of one mirror is somehow switched to the other mirror or affects the other mirror. That's not a systematic error. This is quantum mechanics. Very weak, very statistical, but it's not an error.
Okay, are there any further questions? Yes, Raphael.
Me?
Yeah, one more comment here, just remind me missing part of the presentation. If you have a process which wipes out part of the test, why do I think that you get from here indeterminism, quantum indeterminism? Isn't this a new way of looking at quantum indeterminism? By assuming that there is a subtler world in which it is more deterministic, I don't know whether completely deterministic, but it looks indeterministic because of those negative quantities going back and giving you a smooth area in which apparently nothing is happening. That was one of the other perhaps, one of the last perhaps.
Yeah, before I ask the question, I just want to say that we've been hearing a lot about one vector and two vector formalism, but no one considered the zero vector formalism. That's the one that I think is actually right. So I think we'll hear something, maybe Adrian's talk, and then, in other words, a history-based formalism with the state vector plays no or a very minor role.
Okay.
It's just a comment. But so I'm still confused. I think you said it, but maybe I can just try and repeat and see if I've understood. Your point of view is that someone could, when technology gets sufficiently good, maybe in a few years, perform an experiment which would, the results of which would be exactly as predicted by ordinary quantum mechanics, but would be so bizarre if you interpreted it in the usual one vector language that we would be forced to accept the retrocausality or the two. Is that the point of view? And if that's,
You wouldn't be forced.
well, you would be okay. But you would find it difficult
I
to.
would say, yeah, my idea.
So could
is
you
that-
give an example? I mean, I know you said you don't have such an experiment, but something there was supposed to indicate what it might have been. I didn't get it. Can you just give it a
Yeah.
sort of a rough idea?
You remember I characterized Bell's proof as a proof for the emptiness of the past.
Yeah, I didn't know what you meant by that. Okay.
So here is an opportunity to elaborate on that.
Yeah.
Bell actually tells you that you cannot ascribe. There is a human being or two human beings making choices at the last moment, which out of 2 or 3 measurements they are going to carry out on the particle within the terra that they have. So Bell actually proved that the correlations cannot be ascribed to something that happened before these two guys made the choice. So far everything is correct. So this is why I call it emptiness of the past.
That's what you mean by emptiness of the
Right.
past. You mean you can't.
No to the local.
Right.
Okay.
I just gave it a more exotic emptiness because local hidden variables existed, and if you say that there are no, so the past was empty. And then I hope that you will see some kind of vacuum, such that if later you find out that there were traces of that future in the past, you will argue that there was some kind of vacuum such that when the becoming came to that choice, it went back and affected it. And what I thought is the following. Bell's inequality holds for discrete values, either spin up or spin down, whereas weak measurements show you all the results in between, together with all the noise. Could it be that there would be an inequality sensitive even to such cases that will make the emptiness of the past even stronger, and then will force people to invoke some conspiracy between errors or systematic errors? That they won't be incorrect. It will be just like in thermodynamics to assume that ripples can form in a pond and converge together to the middle and eject a stone, eject a rock out of it. Am I asking too much in hoping that some kind of proof like that may come out? Raphael?
You want me to answer the question?
Yes. Intuitively.
Intuitively, yes.
Okay.
We'll see. Yes. You want me to answer?
Next
I
conference.
think on that devastating point, we have to bring the session to a close. And we'll now go for a slightly shorter than advertised lunch break and resume the next session here at 2. So let's thank our speaker again.
Thank you.